Good afternoon. My name is Mariusz Dąbrowski and I am the president of the Jerzy Stelmach Eureka Foundation. We deal with interactive education and in particular with the popularization of the frontal scientific research. This is due to the fact that we gather at the foundation active scientists and due to this we are able to offer you some lectures and debates under the project Science, in general project Science and Technology Progress Closer to the Society, which is co-financed by the Polish Ministry of Science and Higher Education. These days, we run the session entitled Dark Universe, Problems of Contemporary Cosmology. The session will be held in English and also in Polish, but these lectures, which are in English, will be translated into Polish and placed on YouTube channel in a couple of days after the session. This is due to some technicalities which we cannot avoid. I am pleased to announce that today's second lecture is given by our guest, Professor Salvatore Capozziello from the University of Napoli. Hello, Professor Salvatore.
Hello, Marius. Hello, everyone.
Before I let Professor Salvatore Capozziello to say us something about the nature of dark energy, I would like to mention the most important issues related to his scientific career. Professor Salvatore Capozziello is a full professor of General Relativity and Cosmology at the Department of Physics of the University of Napoli, Federico II. And he also served very important position in relativity because he was the president of the Italian Society for General Relativity and Gravitation, SIGRAV, sorry. He is now the coordinator of a PhD program in cosmology and space science at the Scuola Superiore Meridionale in Napoli. But not only that, Professor Capozziello teaches general relativity at Gran Sasso Science Institute for Advanced Studies in L'Aquila, and he is also a honorary professor at Tomsk State Pedagogical University. Professor Capozziello is also a fellow of the Accademia Nazionale di Scienze, Lettere et Arti, Napoli, Italy, and the Serbian Academy of Nonlinear Sciences in Belgrade, Serbia. It is interesting that, also very good record, I would say, that he has already supervised more than 40 PhD students. Among them, our previous lecturer from today's part of the forum, Professor Vincenzo Zalzano. Professor Capozziello spent some time during his scientific career in very renowned institutions, scientific institutions worldwide, among them in USA, Germany. He was also visited in Poland, United Kingdom, Russia, South Africa, Canada, Brazil, and also Japan. So he was almost everywhere for longer periods, for shorter, I guess, also in some other countries. His main research topic is general relativity, cosmology and relativistic astrophysics in their theoretical and also phenomenological aspects. The latter are sometimes much more difficult than even the former. One of his research is devoted to the possibility of explaining the dark energy and dark matter phenomena by some geometric invariants which extend Einstein's general relativity to more general classes of theories. The results of his research are published in an amazingly more than 700 papers in good research journals, and these papers reaching an amazing number of nearly 35,000 citations, with the so-called Hirsch index being 87. Professor Capozziello is also an author of monographic texts on extended theories of gravity, on gravitational lensing, cosmology and general relativity, editions Cambridge, Springer, Bibliopolis, Liguri. Also, Professor Capozziello, as I mentioned also during the last talk, is 2% top scientists of the world, according to the list of Stanford University. And also, which is very interesting, because it's interdisciplinary too, is that he is among the top 10 Italian scientists list for the last 2 years, 2024 and 2025. Now, let us come to the lecture. Professor Capozziello, the screen is yours. Please tell us about what is the mystery of dark energy and the speeding up of the universe. So the screen is yours already. Okay, we have the presentation.
Thank you so much, Marius, for this very, very amazing presentation. And I'm very happy to stay with you and to present you some of the most intriguing and the most interesting mystery of the universe, which is connected with the fact that there is something dark, which is dark energy and dark matter, and we want to understand what is it. Okay, so before starting with the main topic of our discussion, I would like just to trace a very short story on how we can arrive to the expansion of the universe and how we can deal with dark energy and dark matter as the two mysterious components of our universe. Okay, so let us start very, very easily from what all of you knows very well, the Newton universal gravitation law. Because we will see that starting from this, we have a fantastic and amazing tool in order to understand our universe. So all of you knows the story by the apple falling down, and the fact that after this, Isaac Newton realized that there is an attractive force, and every two bodies which are suffering this force can be attracted proportional to a given constant, which is this universal gravitational constant, and with the distance between the two bodies, which is the one into his Earth. So why it is so important? Because this force is the first major unification in physics. Because after Newton, we can say that terrestrial phenomena, so the falling down of bodies, and celestial phenomena, like, for example, orbits of planets, are exactly described by the same interaction. And such an interaction is the gravity. So we can say that every particle in the universe attract every other particles with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This is stated in the Principia Philosophiae Naturalis, which is the masterpiece by Isaac Newton, written in 1687. Okay, so all of you knows this, but this is the starting point, the very starting point, in order to construct our picture of the universe that we are going to sketch today. So, also, if it is very successful, there are some shortcomings, some limits. The limits is essentially this, that the absurdity that also the same Newton discovered was the fact that imagine that you have two planets, one planet, a big planet into the universe, and at a certain point appear another planet. What is the time in which the second planets and the first planets realize the existence of the other one? These planets is essentially perceived immediately, instantaneously. So there is no limit for the speed of the interaction. On the other hand, there is a conflict with this because before Newton, Galileo, and after Fizeau and Rømer discovered that the speed of light is finite also if it is very, very high. So the conflict put in evidence the fact that this kind of interaction cannot be the final interaction describing gravity because there is no limit for the speed of the interaction. Okay, so according with this, something more is going on. I want to trace back the story of what we consider the observed universe. And this can be connected with another big guys, the other big person, which is Albert Einstein. At a certain point, Albert Einstein realized a very, very important things. There is a very nice thought that he said the happiest thought of my life, in which Einstein wondered that what happened to a person in free fall inside an elevator. So the revolutionary intuition by Albert Einstein is the fact that if you have an elevator in free fall or you have a stationary elevator, the situation is exactly the same. So exists a situation in which you can take the acceleration and then the forces equal to zero. So if you sketch this in a very, very silly way, you can see that if you have a spacecraft and you take into this spacecraft the apple by Newton and you do the same on the Earth, the situation is exactly the same. And then you can say that these two situations are exactly the same. This is a consequence of the fact that the inertial mass and the gravitational mass of two bodies are the same. So Einstein realized a very important issue, which is the fact that the force is not an absolute criterion in order to determine the phenomena. In particular, he stated at a certain point that the gravity is not a force, because the instantaneous attractive force cannot exist. Also, if it acts between two bodies, it requires a way, a medium for the transmission. So he realized another important issue, which is this, that very likely it is the geometry which is determining the motion of the bodies and the phenomenon that we call gravity. So in some sense, he realized that exists a paradigm. because matter tells space-time how to curve, while space-time tells matter how to move. And then, according with this, he realized that the true and very important structure connected with the gravity is essentially due to the fact that the space-time is a dynamical quantity. Why this is important? Because before Einstein, space and time was given. God-given space and time, and phenomena are on the space and time. While Albert Einstein realized that space and time are dynamical, is a dynamical structure, and it determines the gravity, and then gravity is nothing else but the curvature of space and time. This means that the mass can curve the space and time. The curvature is nothing else but the depression of the fabric representation of curvature of space-time, and the motion is essentially the fact that as soon as you are curving the space-time, this gives rise to the motion of body. Okay, so we are constructing the ingredient by which we want to realize the structure of our universe. It is very interesting that in this fabric of space-time, there is an important concept. This important concept is called geodesics. So the geodesics is the shortest line that can connect to observer, to things in the space-time. So, according with this, you can have a geodesics, which is a straight line if you have a flat space. On the other hand, this can be a curved line, but this means that it determines the motion of the object. Okay? So, in this picture, you can find out what is called the Einstein field equation. I don't want to enter into the technicality of this, but I want just to say you that in the left and the side, in the left side and the right side is written nothing else but the fact that the curvature of the space-time is determined by the distribution of matter. It is interesting from an historical point of view to say that this was an intuition by Bernard Riemann. Bernard Riemann, in his PhD thesis, wrote this interesting sentence. He said that the distribution of celestial bodies was determining the structure of space and time. Albert Einstein was very impressed by this sentence, and he tried to realize this, and then he got this very famous equation, which is the Einstein field equation. Please take care about these terms, which is in the middle. This term is called the gravitational constant, and his story is very controversial at the beginning, but as we will see, the dark energy and the dark universe that we are going to describe start exactly by this new element that Einstein introduced for the fact to stabilize his construction, his universe. Okay, so we can say that matter tells space-time how to curve. When matter says to the space-time how to curve, the space-time tells matter how to move. And how matter can move into the space-time? It can move along geodesics. So, in some sense, we can say that since matter is curving space-time, the space-time is guiding matter. And then it means that if you have a body in free fall, it is moving along the matter, and the dynamical object which gives rise to this is the curvature. Then what you can say? You can say that also, for example, everything can be affected by this curvature. In particular, the success of the Einstein general relativity was essentially due to the fact that it is capable to explain, for example, the precession of the orbit of Mercury. Why? Because there was a big controversy which lasted more or less two centuries, in which people cannot realize why the orbits of Mercury was not closing after a given round. And the prediction was that this kind of precession can be explained and confirmed by the Einstein field equation. On the other hand, if the space-time is curved, if you have the light that is passing nearby a given celestial body, you can have that this kind of light can be deflected. This kind of prediction has been observed, for example, in 1919 by Arthur Eddington, which exactly calculate the position of a star during an eclipse. And this was the main confirmation of the general relativity by Einstein. So this gives rise also to a very interesting branch of astronomy. This branch is the so-called gravitational lensing. The gravitational lensing essentially is saying us that when the light is passing nearby a massive body, for example, a galaxy, a quasar, this light is curved, and then the way in which such a light is curved can give us the possibility to map the masses into the universe. So you understand immediately that for an astronomer or a cosmologist, this is a very important tool in order to say when and where the distribution of mass is located. This is one of the main results connected with general relativity. Another important result, which has been discovered very recently, 10 years ago, is the fact that space-time, being a dynamical object, can also give rise to waves. And these waves are called gravitational waves. They can be said as can be so as a sort of ripple of space-time, and they are generated by extremely violent cosmic event. For example, if you have a black hole, a very massive star, which is moving each other, they give rise to they are source of these gravitational waves. In particular, there was a very interesting event in 2015 by which two black holes, I will show you in a moment, give rise to the big production of these gravitational waves, and they has been detected. These objects are moving at the speed of light, and they discovered was, in my opinion, the best confirmation of the fact that the general relativity is a very well established theory. In particular, what are the characteristics of these gravitational waves? These gravitational waves has two polarization. Technically, they as a quadruple. So being a quadruple in nature means they can be generated by some deformation, and then they are generated by tidal effects of some astrophysical object. But in order to give rise to these gravitational waves, you need very, very compact objects, as for example, black holes, neutron stars, and so on. So another confirmation of this is the fact that this kind of object has been recently detected. In particular, these gravitational waves give rise to the so-called new window in the universe on the so-called multi-messenger astronomy. This is an interferometer by which it is possible to detect this kind of gravitational waves. And the important point was this. In September 14, 2015, happened this discovery. This discovery has been done contemporary in two places which are distance more or less 2,000 kilometers, which are the interferometer in Hanford and in Livingston in the United States. Both of them registered this kind of signal that you can see here. And this is essentially the signal that they revealed. But the important point is the fact that in both places, as you can see here, they detected exactly the same signal, which is reported here. And essentially, after very, very important and very, very fine theoretical reconstruction, scientists realized that this kind of signal has been generated by the inspiraling and the merger of two very massive objects of the order of 30 solar masses, which are two merging black holes. Okay, so after this, you can say that the gravitational waves means that this ripple of space-time can move, and we will see that they are very important in order to construct our picture of the universe. In particular, what they detected? They detected that there was a black hole of the order of 36 solar masses. There is another black hole of the order 29 solar masses. The final black hole was of the order of 62 solar masses, and the remnant of this was given by the energy of this extremely massive and very energetic phenomenon, which was essentially the production of the gravitational waves. Okay, so now another important point in order to construct this vision is essentially the presence of a black hole. What is a black hole? A black hole is an object extremely massive, which is so massive that also the light cannot go out into the black hole. And if light or particle are entering into the black hole, they cannot escape from this. So essentially, this is in some sense the fact that this kind of black hole, imagine that has been forecast for the first time in 1916 by Carl Schwarzschild, which was the first that had the intuition and solved the Einstein field equation that I showed you before. And after this, they remained, in some sense, for more or less 1 century, a sort of theoretical object that no one has detected. But in 2019, the Event Horizon Telescope collaboration has essentially get a snapshot of this kind of black hole. So the black hole and the gravitational waves are the two main ingredients that give rise to the fact that the general relativity is a good theory and is working in a very predictive way and could be used in order to model out any gravitational structure. So after this preamble, we can go to our main topic. Our main topic is this. Cosmology and then the whole universe can be represented according to the laws of general relativity? And the answer is yes, because in the October of 1917, Einstein gave a very important lecture in the Kaiser Wilhelm Institute in Berlin called Cosmological Considerations on the General Theory of Relativity. And scientists say that this is the born of the scientific cosmology. Why? Because before Einstein, cosmology was considered something related with metaphysics, because no one can understand how the universe can be constructed. And so cosmology, like metaphysics, could be nothing else but something that could be in the realm of philosophy. But starting with this kind of consideration by Albert Einstein, he applied his equations to a dynamical system, and such a dynamical system is the universe, the whole universe. So in order to do this, the universe has a story, has an evolution. Why? Because the Einstein field equations are dynamical universe. At the beginning, Einstein had in mind the fact that the universe should be static. And then, according with this, he proposed the existence of a cosmological constant, because such a cosmological constant should stop the evolution of the universe. And he said at a certain point that this was the big blunder of his life. Why? Because soon after, these guys, which is Edwin Hubble, make a fundamental discovery. He discovered between 1924 up to 1929 that galaxies are receding with respect to us. And then he said that due to the fact that galaxies are receding, the universe is expanding. So, like a balloon which is expanding, the galaxies are moving away from each other, and then this is essentially due to the fact that the same space is expanding. So, in some sense, Edwin Hubble realized that the universe is really a gravitational dynamical system. Okay, but this idea, this intuition related with this observation was formalized by these four guys, which are Alexander Friedman, Georges Lemaitre, Robertson, and Walker. They realized that the whole universe can be described as an homogeneous and isotropic fluid. This is the famous Friedman-Lemaitre-Robertson-Walker metric, which is the way in which you can describe this object and this universe in time. And then you can see that the ingredient of this equation are nothing else but the fact that the universe is expanding in time. Its scale factor means that its volume is improving with this kind of expansion. There could be a spatial curvature, and the angular coordinates are essentially saying where it is the position of a given object, in particular where there is the position of a galaxy. This means that our universe is homogeneous, isotropic, and expanding. And several probes for this statement has been realized starting from the 30s of the last century up to now. In particular, we can establish, and we will give details on this, on the modern cosmological models are essentially some model in which you can say that there is an origin, there is an expansion. The up to now has been calculated with some details, the very big details, sorry, the age of the universe, which is between 13 and 14 billion years, and there is an origin, there is an evolution, and today the universe is continuing to expand. And we will see that some observation, in particular the dark energy spectroscopic instrument and the forthcoming Vera Rubin observatory, are giving now crucial data in order to say that this picture is working. Sorry. Okay, so let us start with this kind of discussion, considering the beginning. The universe started approximately 13.8 billion years ago, according to the observation. And it started with a big explosion, and this explosion is the fact that the same space-time is expanding. This is called the theory of the Big Bang. And the one that gave the origin of this theory of Big Bang was Georges Lemaitre, that in 1927 was the first that forecast this kind of evolution according with the law, the metric that we described before. In particular, this means that there exists an epoch which is called the Planck epoch, Planck era, in which the universe is so thin that it cannot be described by the classical law. The classical laws means the fact that it is expanding and it is just following the laws that you have in standard physics. But in that case, you have to take into account the quantum law. So at the very beginning, in a very teeny period, which is 10 to minus 43 seconds, the universe is essentially dominated by quantum phenomena. Also, the same space-time is not a continuum, but is nothing else but a quantum form in some sense. Soon after happens the so-called cosmological inflation. What is cosmological inflation? Is the fact that the fields and the distribution of matter into the universe give rise to a expansion. And such a super expansion enlarge at the very beginning a lot the primordial universe. Then, what happens? Happens that at a certain point you can take into account a sort of primordial soup. In this primordial soup, several particles are going to be formed. In particular, we can have the elementary particle that we know, the proton. Before proton, you have quarks, gluons, which are the constituent of the neutrons and protons that we have now. We have a very extreme temperature, very hot. The universe, the early universe is a very hot place. And there are that all the fundamental forces can be considered as the same force. So people is saying that in the primordial universe, you have exactly the same interaction, and then you cannot distinguish between gravity, between electromagnetism, weak force, and strong force, which are those related with the particles, but you have just one interaction. And furthermore, the primordial universe is dominated by matter and antimatter. Matter and antimatter are essentially the same thing, but the charge is the different. For example, you have an electron. The electron has a negative charge. A positron has the same as the electron, but with a positive charge. So this means that matter and antimatter share the same situation at the beginning of the universe. At certain point, when this system is going to enlarge and then is going to freeze out, several particles are going to be formed. In particular, the first step of this is the formation of protons and neutrons, which are those particles which constitute the stars, the galaxies, and also the human being, essentially. Okay, this means that the quarks combine and give rise to hadrons, which are protons and neutrons, essentially. And this is essentially the picture that you can give rise. Soon after, there is a very important event, which is called the Big Bang nucleosynthesis. And such a primordial nucleosynthesis gives rise to the atoms that we are observing, which are essentially hydrogen, deuterium, helium, and some trace of lithium. So this means that as soon as this universe, this dynamical system, which is the universe, is expanding, and after the production of the elementary particles, also the atoms are going to form. And then immediately you have the formation of the very simple elements, which are essentially the hydrogen and the helium and their isotopes. Okay, so as you can see, this process is very rapid because it lasts more or less 200 seconds. So after this, you can have some reactions. This kind of reaction are essentially nuclear reactions, which give rise to the formation of the deuterium, of the helium 3 and helium 4. So as you can see here, you can have that if a proton interacts with the neutron, you can give rise to the deuterium plus a photon. On the other hand, you can have deuterium and deuterium and giving rise to the isotope 3 of helium, and so on. So this means that this nucleosynthesis is going to produce the elements that we are observing into the today universe. Okay, but we will see that these are the cosmological elements, so they are produced at the very beginning of the universe, while the vast majority of the elements are produced inside the stars. So when people say that we are sons of the stars, is true, because in stars all the elements that are constituting our bodies, in particular the carbonium and so on, the carbon and so on, all of them are produced inside the stars. So, at the end of this early process, you have the so-called primordial nucleosynthesis, which give rise to the so-called abundances of the early elements, which are essentially 75% of hydrogen, 25% of helium, and then you have some traces of deuterium and helium. So, as you can see, the universe is not only a dynamical system, but it is also a chemical system, because inside this universe, all the elements that we are observing and we are testing in our life are produced. So we can say that the universe is a dynamical system, a thermodynamical system, because its temperature is determining the various phenomena, and is also a chemical system because of the production of the elements that we are observing. So, at certain point, we have a very interesting situation. We have the so-called opaque universe. The opaque universe is the fact that after 380,000 years after the Big Bang, this soup of the Big Bang became so dense and that light cannot escape from it. So in some sense, we have a situation in which the production of the element is preventing the light to go out and then to have a luminous universe. While at certain point, you have the so-called recombination. The recombination means that these particles are producing the elements that and the atoms that we are observing, in particular hydrogen and helium, which are the main constituent of the stars. So after the recombination, we can have two very important phenomena. The first is that the universe became transparent to light. So in the Bible is written fiat lux. When we have fiat lux means that you are at the recombination. In this sense means that the gamma rays and then the light rays are in some sense emitted by the atoms, and then they give rise to the possibility that the opaque universe that we have seen before became a transparent universe, and then it became a luminous universe. This phenomenon is extremely important because it is connected with the main probe that we have for our universe. This probe is nothing else but the cosmic microwave background. What is this? Is the fact that you can imagine our universe as a sort of black body. In this black body, you have, because you can suppose that the universe is not connected with other universe, so is an insulated system. And then this insulated system have a particular temperature. In particular, you can see that today the temperature, the whole temperature of the universe is of the order of 3 Kelvin degrees. So to 3 Kelvin degrees, you can have a cosmic microwave background, and this is a very formidable probe for our universe because observation of this kind of background give rise to the possibility to reconstruct the whole story of the universe. And if you see the spot that you have here, the spots are the seeds of the large-scale structure that we are going to observe into our universe. In particular, at certain point, you have that this cosmic microwave background give rise to a so-called period of the dark age. What is this dark age? This dark age is the period in which all the materials that has been produced before is going to be accumulated, and when it is accumulated, it gives rise to the stars. And when stars became brilliant, according with this, you have at the end of this dark age, the possibility to see the presence of stars. So the universe was essentially dark and opaque for the shorter wavelengths due to the absorption of these hydrogen atoms. This is connected with a very interesting phenomenon, which is the fact that it is connected with what we are going to observe in the universe are essentially galaxies and clusters of galaxies. And then these cluster galaxies are nothing else but the evolution of the primordial perturbation that we have at the very beginning. It is interesting that the cosmic microwave background, the spots that we have seen in the cosmic microwave background can be connected with the large scale structure that we are observing today. So the large scale structure is nothing else but the evolution of the primordial perturbations that give rise to what we are going to observe today, which are essentially the main structure that we have into the cosmos. So, at a certain point, we have the formation of stars and galaxies. They are extremely important because stars and galaxies give rise to the lights that you have into the universe. So the first stars are something very massive, and they have masses of the order of 30 up to 300 times with respect to our sun from one side, and galaxies, the first galaxies are nothing else but agglomeration of this kind of primordial stars. And then we have another important phenomenon. I am just to tracing you the history of our universe in order to understand why you can have this kind of evolution. And we are going now to finish with our dark energy and dark matter. So the reionization means that at certain point you can have that the light inside the atoms can be gradually can ionize the hydrogen atoms present into the gas. So this reionization is extremely important because it happens about 1 billion years old after the Big Bang, and this gives rise, for example, to the fact that the universe became again transparent to the light. So the reionization is a very important phenomenon in order to make observation into the realm of electromagnetic band. So all this stuff can be connected with what we mentioned before, the Hubble discovery. Why the Hubble discovery is extremely important? Because this American astronomer in 1929, but starting his research in 1924, discovered the fact that more distant galaxies are moving away from us at a greater speed than closer one. This means that if an object is very far from us, it is moving faster than an object which is nearby us. So if you sum up this kind of observation, you can deduce that the universe is a fluid and such a fluid is expanding. So this discovery, in some sense, could be the basis of the observational cosmology, which can be related with the discovery from a theoretical point of view that we have seen with respect to the Friedmann-Lemaitre-Robertson-Walker metric. In some sense, the Hubble law is stating that the Friedmann-Lemaitre-Robertson-Walker metric could be connected with this homogeneous and isotropic expansion. In particular, the law that recently has been called the Hubble-Lemaitre law, because also Georges Lemaitre discovered, is nothing else but this. If you have an object which is moving from us, which a given velocity v, you have that such a velocity is improving with respect to the distance. And This H0 is the constant that you can immediately realize that is the inverse of a time, which gives us the possibility to have that as soon as you have a very distant object, it is moving faster and faster if the distance is improving. This law is extremely fundamental. Why? Because this law can be connected with the cosmological equation deduced by the Einstein field equation from one side, and this law can say us also how much matter and energy is distributed all over the universe. So it is really a fundamental law of nature, which is connected with this very, very simple equation. In particular, after this, you can construct the so-called standard cosmological model. Which is the standard cosmological model? And now we will go directly to the topic of this lecture. Is the fact that the cosmological fluid is expanding. You have a very thin amount of ordinary matter, which is of the order of 5% of the universe, while the largest part, it is the fact that you have an accelerated expansion of the universe, and this is connected with the dark energy. While the dark matter is the fact that in order to give the clustering of the structure that we discussed before, in order to have this, you need a large amount of matter which is gravitating, but which cannot be connected with the fact that it is emitting light. So you can state that our universe is essentially constituted by a very little percentage of ordinary matter and a large amount of dark energy, which give rise to the expansion, and dark matter, which give rise to the clustering and then to the large scale structure that we discussed before. Clearly, now we have a problem because at the moment we have no final statement on what is dark energy and what is dark matter. So you have, and this is a very recent discovery, that we expect that if you have a fluid and such a fluid is expanding, the first speculation says that this fluid is expanding and then it should slowing down, and then it should be a decelerating fluid. But was not this the case, because has been detected in 1998, and according with this, this discovery earned the Nobel Prize in 2011. They discovered the fact that the cosmic fluid, instead of decelerating, is accelerating. And this has been detected according with the fact that there are some standard candle. It means that some objects which are emitting a lot of light, in particular this supernovae, which are accelerating instead of decelerating with respect to us. So how they and why they discovered this? They discovered this in this very simple way. Imagine that you are on the Earth, and imagine that this is a galaxy, a far galaxy. If such a galaxy is receding with respect to us, the light emitted have this Doppler shift. The Doppler shift is connected with the fact that the light is going toward the red. And going toward the red means that the source is going far away with respect to you. So the large amount of this cosmological redshift is the probe of the fact that the universe is expanding. But in order to understand this, we have not enough standard matter in order to have an explanation for this. So people invented the so-called dark energy, that at the moment is a mystery, because we are not capable of saying what is this kind of fluid giving rise to this kind of phenomenology. But Related with this, we have several problems. In particular, we have the so-called cosmological tensions. What is a cosmological tension? The cosmological tension is the fact that if you want to measure the parameters which are connected with this kind of picture of the universe, you realize that this kind of parameters, in particular the Hubble constant, measured in the local universe or measured in the primordial universe, are different. And the discrepancy between the measurements is very high. And then, according with this, there are some problems. Or the cosmological model is wrong, or there is something which we are not capable of addressing with this kind of picture, which give rise to the fact that the cosmological constant and the Hubble constant are different in the various epochs in which we are going to measure them. In particular, what is the Hubble tension? The Hubble tension is the paradigm of this kind of tension. As we have seen, the Hubble tension enter into the Hubble-Lemaitre law, and this is a fundamental parameter which says us how far are galaxies with respect to us. This parameter, being related with the inverse of a time, is extremely important in order to deduce the age of the universe. If you remember, we said that the age of the universe should be around 13 and 14 billion years. But if you measure the Hubble tension taking into account, for example, the cosmic microwave background, you get this kind of measurement. 77 kilometers per second per megaparsec. The megaparsec is essentially a cosmological distance this way. But if you do this in the local universe, you get 73. Then you can say that the age of the universe could be different if measured with respect to the cosmic microwave background from one side, or if measured with the supernovae, which are in some sense near to us. So the discrepancy is so large that we have this kind of situation. Probably we have to invoke some new physics in order to justify this very interesting and very strange this mystery, or in some way you have to find out some form of dark energy capable of addressing this problem. In this sense, it means that the implication could be extremely delicate, because they give rise to the fact that the standard cosmological model that I described before could be extremely different if you consider it based on local observation from one side, or with the observation which are connected with the cosmic microwave background. So the comparison of this H0 could be different according with this kind of picture. There are other tensions. In particular, another one is very important, which is the sigma 8 tension. What is this sigma 8 tension? This sigma 8 tension is connected with the fact that if you remember the perturbation that you can detect into the primordial cosmic microwave background, they are connected with the fluctuation of matter that give rise to galaxies, to cluster of galaxies, and so on. So the amplitude of this matter fluctuation could be different if you measure it with different probes and with different observers. And then you can say that also in this case, this kind of tension could be connected with some form of dark energy and dark matter. If you compare this kind of measurement, now it is a very technical, but it is extremely important, you can say that the clumpiness of the universe could be determined by the amplitude of the matter fluctuation. And then you can have that the clustering of galaxies could be different with respect to the measurement of this sigma 8. So this means that both the H0 parameters and the sigma 8 parameter could give rise to very different picture of the universe. When I say different picture, means the size of the universe, the age of the universe, and the way in which it is expanding. Okay? So there are several possible explanations. These are very hot topic for the modern cosmology. In particular, they could be related with some systematic errors. You can have errors in calibration, in the modelization, in the correlation, in the various assumptions. And this could be, in some sense, related with the fine observation that people is setting up. But there is another way of thinking in which they could be, in some sense, the fact connected with the fact that they could be connected with some new physics. There is something which we do not understand and that we simply call dark energy or dark matter, but they probably could be new particles or something which we cannot understand. Or very likely it could be connected with a new theory which is enlarging, which is extending the general relativity with respect to the standard Einstein proposal. Because why this could be? Because we are pretending that the general relativity is working from the Planck size at the very beginning of the universe up to the end of the universe. So it's a very large numbers of degrees order of magnitude of this kind of phenomenon. And very likely we are extrapolating the same law of physics that probably should be modified or extended at the various scale. So I think that this is nothing else but a picture, a snapshot of what is going on. And this is connected with the history of the universe. So in particular, very likely we need some new form of dark energy. We have to modify the gravity. We have to consider some interaction, new interaction. We need some neutrinos of some form of warm or cold dark matter. So there is a plethora of proposal. Why there is a plethora of proposal? Because as at the moment, physicists and cosmologists cannot explain into a unitary picture all the phenomenology that we are observing. So the universe today can be described, as I said, in a structure which is an age of the order of 1380 billion years. And this kind of fluid can be composed by dark energy, dark matter, and ordinary matter. But if you ask me what is dark matter and what is dark energy, I can say you that dark energy is the phenomenon giving rise to the accelerated expansion. Dark matter is the phenomenon giving rise to the clustering of the structure. But if you ask me at fundamental level what is dark matter and dark energy, at the moment I have no answer. So this means that we have to investigate this kind of component not only at astrophysical and cosmological scale, but we have to investigate this kind of structure also at very fundamental physics. So at the physics, with the physics of the accelerator, or with the physics of the direct detection of this new form of particles. So why it is extremely important having fine observation? Because future experiments and future observation could give rise to a huge amount of data by which it could be possible to reconstruct in a very detailed way what we discussed up to now. So at a certain point, we need to improve our research and to get several funds in order to realize this kind of observation, because they could help us to solve this kind of tension and this kind of mysteries. So in conclusion, we have that our universe as a paradigm is well established, but there are several shortcomings and several tensions that need to be addressed with very finest in a very finest approach. So, in conclusion, the standard cosmological model it is highly successful. And because for sure we have that the universe is expanding according with the Hubble law. The cosmological redshift has been detected. The accelerating expansion has been detected. But the tension are the fact that several parameters can give rise to some misunderstanding and to some shortcoming by which the picture is not self-consistent in all the epochs in which we pretend to give the history of the universe. So I think that cosmology stands on the bricks of a new scientific revolution because, as you can say, we can say, for example, that fundamental physics is in some sense correlated with cosmology and vice versa. So, thank you for your attention, and I hope that I give you a taste of the mystery connected with understanding the cosmology.
Thank you very much, Salvatore, for this very comprehensive review of the ideas of dark universe, and it's probably the correlation with the fact that you also got very dark in your screen. Probably it's due to the fact that it got dark in Italy already. Here in
Exactly.
Poland, it's a bit still almost dark. Okay, so you tuned to the atmosphere of the dark universe, which is
Exactly.
kind of a very interesting story. Okay, we have one question. Okay.
As you see, I put here the venerable Yoda because probably he knows the answers.
Yes. Okay. Okay. The
Okay.
question is, I wonder what is your opinion on some new ideas explaining the effect of Hubble's tension to some differences in the passage of time in different regions of the universe. As we know, the theory of relativity revealed that simultaneity doesn't exist, and in fact, time must be different in each and every part of the universe. That's
Okay.
the question to you.
Okay, very interesting question and very, very, very subtle question. My personal opinion is this, that we are just trying to make an extrapolation because we like that everything that we measure here is the same that we can measure up to the end of the universe. And I think that in physics, this approach is not good because we pretend, for example, that the measurement of the gravitational constant is the same here, given with the torque pendulum at the Cavendish in a Cavendish way, and we pretend that the value of g is the same here and up to the last scattering surface. My personal idea is that we should demonstrate that gravity is not scale invariant. And then, according with this, we can try to explain the various tensions that we have. Why I'm almost convinced about this? Because the particle of physics, the standard model of particles, I try to give a picture of the standard model of cosmology, but the standard model of particles is very, very well posed. And the discovery of the Higgs boson is in some sense saying that the three family of particles already detected are very hard to be improved with other particles because up to now, imagine that the Higgs boson has been discovered in 2011, but today, in 2025, there are no probe for other particles which can be connected with the dark matter or dark energy. So my opinion, the only interaction on which we can work is gravity. So I think that we are in a very interesting situation, because very likely we are in the same passage that you have from Newtonian gravity to Einstein gravity. And now we should have something which could be connected with the post-Einsteinian gravity. General relativity is working very well, but very likely at a very large scale than cosmology and a very short scale than quantum gravity, very likely it should be revised. So in order to answer to the question, I think that among the various way to fix the tensions, we have to consider if it can be connected with the fact that the gravitational interaction could be revised at the various scales. I hope to have answered the question.
Okay, so it's related to the suggestion, which actually fits very well my expectations, and I was running even the project in that the physics or the fundamental constants somewhere in the universe not necessarily are the same as in our laboratory here on
Exactly.
Earth. Yes, so this is one of the very nice suggestion, and probably what happens at CMB time is not necessarily the same as is happening now.
Exactly. Exactly.
And one needs to take all this into account. And I think there are theories in which these effects are taken into account.
Exactly.
Yeah.
Exactly. I completely agree with you, Marius. But
Mhm.
very likely this is the point. This is the point. I can give you just to give you my idea on this. I give you a mathematical example for this. You know that the Hubble-Lemaître law is a straight line. Okay, so imagine now that you take into account a parabola.
Mhm.
If you have the straight line, the parabola can be approximated by the straight line immediately, because point by point it can be done. But you cannot continue to approximate these up to very large distances. So at certain point you have to take into account the parabola. So
Mhm.
when you detect the H0 at the scale of cosmic microwave background, you need the parabola, because in that case you have the Einstein field equation. And you know that in that case, the Einstein field equation takes into account h squared, while in the nearby us, you can have the Hubble law is a straight line. So I think that it is also a matter of the approximation that we are doing. For example, there are very recent discoveries, very recent paper by the people that discovered the accelerated expansion, that they say that the Hubble law, if calculated in distant galaxies, could be corrected. So according with this, it could be an hint of the fact that at very large scale, you need a different approach with the gravity, nothing more. However, we have to demonstrate this.
Okay, that makes kind of a clear thing because there is a difference. I mean, if some local measurements gave a different value of the Hubble parameter, and they were in tension, then we would not think of, having time relation or distance relation, variability of the physical laws or constants.
Exactly.
But we have clearly the difference between this and that. It's not the same situation as it happened between in the 90s with the Hubble tension. They didn't call it Hubble tension between the measurement of Sandage and the Vauclair, where
Exactly.
they both were measuring local
Exactly.
objects, and
Exactly.
they got always different values between 50 and 100. It's a different story nowadays because different objects in the universe on the different distance scales are measured. So yeah, your
yeah.
suggestion is probably the most reasonable, unless yes, there is something which we don't know about the methods of measuring. But I think the
Exactly.
methods nowadays, the equipment is so precise that it cannot be
Exactly. It's not a matter of measurement.
yeah, the measurement can fail.
So extrapolation in physics are not good.
Yes,
At
yes,
this point.
that's something which I like because the universe is huge, and I cannot really understand why we can say that far distant universe is the same as here. Okay,
Exactly.
and that everything is the same everywhere in the world, even in
Exactly.
terms of you know, because we had a session about aliens in March this year, and the discussion about aliens also touches this, because the aliens can be different from us
Exactly.
totally,
Completely
even
different.
physically, you know, if they were formed
They,
in the
they
other
can be
parts of
vegetables instead of animals. So who
yeah,
knows?
yeah, yeah. Okay, I
Okay.
don't see any more questions, and anyway, we are a bit over time. So I would like to thank you, Professor
Uh,
Capozziello, for this wonderful talk. Thank you, all the people who are watching us on Zoom and also on YouTube. Thank you that for your presence, and hope that you will still watch these lectures later in both English and after translation into Polish. And I would like to say that you were the guests of the Jerzy Stelmach Eureka Foundation, which presents the series of discussion fora, and this forum is still running, and there will be two more lectures on Monday and discussion on Tuesday, and its name is Dark Universe: Problems of Contemporary Cosmology. Once again, thank you very much,
Thank
and
you.
see you soon
See you
during the
soon.
next meetings related to this session. Thank
Okay.
you very
Thank you
much.
very much for the invitation.
Good evening.
Good evening.